Okay, so today we will be doing a past paper on the solubility of solutes in different solvents. The specific solvent we'll be looking at is water, right? And that is the main solvent we study when we're looking at solubility for CSEC purposes, right? So let's get started with the past paper. The solubility of a solid X in water at various temperatures is determined by the procedure described below, right? So this is the procedure. This procedure comprises a series of experiments numbered 1 to 5, right? So you can see in the table below, the experiments numbered 1 to 5 there. Some of the data are recorded in that table below that I just showed you. So this is the procedure. In experiment 1, 2 grams of X is added to 4 cm³ of water in a boiling tube, right? So let's take note of our amounts, right? We have 2 grams of X and 4 cm³ of water. Right? The tube is heated and while stirring in a water bath until all of X is dissolved, right? So you're dissolving all of X. The solution is then allowed to cool, and the temperature at which the crystals of X first appear, right? The temperature, so this is very important, the temperature at which the crystals of X first appear, sorry about that. The temperature at which the crystals of X first appear is noted, right, and recorded in the table below, right? So let's find that in the table below, the temperature at which crystals reappear. So these are the temperatures, they listed too. In each of experiments 2 to 5, so we are going on the other experiments now, the same mass of X, so the same 2 grams, you're seeing mass of X here, and 2 grams is for all the experiments, is added to a different volume of water as indicated in table 1. So you're seeing the different volumes of water that they added here in this color. In each case, the temperature at which the crystals first appear is displayed on the relevant thermometer in figure 1. Right, so there's a figure below here. Each time they recorded, this figure shows the recordings they got. This is figure 1, right? So one important thing to note, and it's something that is reoccurring in past paper questions for solubility in chemistry, is this temperature at which crystals first start to appear and what it means. It is understanding what it means is key to understanding the question itself and how to approach the question, how to figure out the question, right? So what essentially is happening at the start of the experiment, you are dissolving a particular mass, 2 grams of your solute X in 4 cm³ of water. You're heating to do so, because what we know about solubility is that solubility increases, or it's easier to dissolve your solute at higher temperatures, right? And then as you cool, right, all of the solid is dissolved, and as you cool it, the crystals first start to appear, right? This point at which the crystals first start to appear can be basically the same as the temperature at which the solution exactly becomes saturated, right, and begins to pass that saturation point, right? So at first, you have your test tube with your crystals there, and it's heated up to a high temperature. Let's say, for example, you heat it to about 95 degrees Celsius, right? This is just for explanatory purposes. This is not the exact temperature that you would have used, right? And you have all of your 2 grams in that test tube being dissolved, right? What we are to assume is that this solution heated at this temperature is an unsaturated solution, right? And how we can assume that is because after it's cooled, it takes a while of the temperature decreasing before the crystals start to appear, right? So this solution that we have here is unsaturated. Change the color. Right? That solution that we have here is unsaturated at this particular temperature, right? Because it being saturated or unsaturated will be dependent on the temperature, right? As you lower the temperature, right, you eventually, right, will get to the temperature at which, so you're lowering the temperature, and you will eventually will get to the temperature at which this solution here in the test tube becomes a saturated solution, meaning that this is the maximum amount of the solute X that can dissolve in the given amount of water that is in the test tube, right? So as you lower the temperature, eventually the solution in the test tube will become saturated. Right, and immediately after, right, crystals will begin to appear, right? So this temperature T here that they are recording, right, is the saturated temperature here, T. You can call it, let's say, T degrees Celsius, right? Which those saturated temperatures are the temperatures that you would usually plot on a solubility curve, right? So understanding this now, it's easier to follow through with the question. Right, so the first part of the question, part A, says complete table 1 by 1, first recording the temperatures at which crystals of X reappear in each experiment, right, using the information in figure 1, right, and 2, to determining and recording the corresponding values for the solubility of X, right, and they give you equation to assist in this. So let's do the first part, completing the table by putting in the temperatures, right? So they give you two temperatures, and you are to get the following three for experiments 3, 4, and 5. So let's use the figure and read off the values, the temperature values for experiments 3, 4, and 5. Right? So if you're looking at this scale, it goes from 40 to 50. That's 10 degrees we have between 40 and 50, and they're exactly 10 tiny divisions. So it's simple, right? That each division is 1 degree Celsius, right? So we have 40, 41, 42, 43, 44. Right? This one, we also have 10 degrees between 25 here and 35. So the same amount of divisions. Each division is 1 degree. So we have 25, 26, 27, 28, 29, 30, 31, 32. Right? 32. And here we have the same scale, 10 degrees and 10 divisions, right? So we have 20, 21, 22, 23, 24, 25, 26. Right. Let's just go up and put these values in the table as we would do if we were in an actual exam. You will actually put them in the table to complete the table as the question says. 44, 32, and 26. Right, so that part was fairly simple. It just is based on your ability to read the different scales. So part 2, determining and recording the corresponding values for solubility of X, and you're using this equation to assist. Right, so even though in this case they gave you the equation, they may give you the equation to assist you in other scenarios as well in the exam. But just in case you're in a situation where they don't give the equation, let's look at the equation and understand how they got this particular equation, or why we're using this particular equation, right? So it says at each temperature, solubility of X is equal to the mass of X divided by the mass of water multiplied by 100, right? Assuming 1 cm cube of water is equal to 1 gram of water. So let me go back up to the table. Right, so we are to fill in the solubility values in the table, right? So we know the units for solubility is the mass of X, right? Let me write that in. Units is equal to your mass of X per 100 grams of water, right? So the information that we have to do this is using the mass of X that they have here. They use the same mass of X each time. But this mass of X that they have in this table, right, that they have in this table for each experiment is per a different amount of water. It's not per 100 grams of water, right? And here because they're saying that 100 grams of water is equal to 100 cm cube of water, right? 1 cm cube is equal to 1 gram for water. We can kind of assume grams here, right? So we're using, it's per 4 grams in this experiment 1, per 8 grams in experiment 2, and so forth, right? It's different grams, it's not 100, right? So in order to find the answer in each case, we have to find a way to change this amount to find out not the mass of X in 4 grams, but we need to find the mass of X in 100 grams of water. So we have to convert this mass in some way, right? And we use a technique that we do in chemistry all the time, which is fairly simple, right? I like to use basic techniques for my students to understand, right? And it's basically, right, if you want to find for a certain amount, that certain amount in this case being 100 grams of water, all you do is, and you have for some other value, let's say you have for 5 grams of water, in this case we have 4 grams of water and different amounts. All we do is we find for 1 of whatever we need, and then we convert to find for the amount we actually need, right? So we'll find for 1 gram of water the mass of X in 1 gram of water, and then multiply by how much we need, right? So we'll be multiplying by 100 to find for 100 grams of water, because that is what we need, right? So if we were to do that with, right, and when we look at that, we basically get the same equation they have below, right? Where you have mass of X in 100 grams of water, right? Or, right, slash, we can put this is also the solubility, because we see this is the unit for the solubility, or solubility is equal to, right, so this is the part where we're finding for 1, right? We would take the mass of X that is used and divided by the volume of water that it is dissolved in, right? And this would give you the mass of X that would be dissolved in 1 gram of water. Sorry, I put volume here. It should be the mass of water that it is dissolved in, right? But either way, you would get the same amount, right? Because we're saying 1 gram is equal to 1 cm cubed for the water, right? It's a similar concept with if you are buying oranges in the market and the vendor is selling you 20 oranges for $10, right? And you want to find, right? So let's do that little simple thing up here, right? They're giving you 20 oranges, right? For $10. And you only want 1 orange. Let's say that's how much you want, right? It's easy for you to determine what would be the cost of that 1 orange. Right? You will just take this $10 and divide it by the 20 to get the cost of one orange, right? And that will just be 0.5, right? In that case. So it's the same concept that follows through, right? And now, if per se you did not want one orange alone, but you wanted 3 oranges, right? After you found for one orange, right? Right, so this would be 50 cents for one orange. What would you do to find for 3 oranges, right? It's a 3 oranges, and I'm just putting OR to abbreviate. Oranges will cost the same 50 cents, 0.5 multiplied by 3. Same concept. After you find for 1, so this in brackets is how you find for 1. You now multiply by how much you actually want to find for that amount, right? So multiply by 100, and that is the same equation that we have below, right? That is the analogy they used. So let's input the values for the first one to confirm that they have the solubility for the first one as 50, right? The solubility will be equal to 2 divided by 4 multiplied by 100, right? This is for experiment. Right, experiment 1, right? The solubility is indeed 50, right? When we input those values into the equation, let's just do it for experiment 2. Conversion, the mass of X is still 2. As we see there in the table, it's 2 grams. So we have 2 divided by the mass of water it was dissolving. You get from the table that it's 8 grams, right? And you multiply by 100 to find for 100 grams of water. And when you input these values into your equation, your calculator, sorry, you will get 25, right? You can do the same thing for all 5 experiments. Plug in your values and you will get the solubility. 25, let's type it. 25. For the third one, you should have 16.7. For the fourth, you will have 12.5, right? That's grams per 100 grams of water. And for the final one, should have 10, right? And that should complete showing all your working though. Part 2 in E, right? Let's just note that this equation is at a particular temperature because the solubility changes at a particular temperature. You see at each temperature, right? The solubility changes. So you can't use the solubility you got at one temperature and apply it to a situation where your solution is at another temperature. So part B, now we're moving on to using the axis on the grid provided on page 5. Plot a graph of solubility of X against temperature in degrees Celsius, and you're drawing a best fit line through all your points plotted. Right? So let's go to the grid and see if we can quickly plot our points. We have to understand the axes that they give us. So our first point should be at the temperature of, right? Temperature is below solubility, exactly, right? Temperature. So at the temperature of 91 degrees Celsius, right? So 10 degrees, 10 divisions. So each division, right, each division will be 1 degree Celsius, right? So 91 will be right here, right? We scroll up now to get our solubility point, which will be 50, right? So our point will be drawn right there. The second point, 57 degrees Celsius, right? 55 will be here, 56, 57 will be there, and 25 for the solubility, right? And 25 will be midway between 30 and 20, which is right here, right? 57 and 25. Second point, right there. Third point, 44 and 16. 44 here, 41, 42, 43, 44, and 16, right? So we have here now we have 10 units here for the solubility, right? The difference between 10 and 20, it's 10, right? Little unit solubility units there. And instead of 10 little blocks, we have 20 blocks. So each 2 blocks is 1 solubility unit, right? So after midway will be 15, right? And we're looking for 16.7, right? 15 here will be 16, and we'll approximate it at 16.5, right? Which will be right there. Just recheck that. 15, 16, 16.5, right? So we have approximate, right? We could draw it a little bit above the line if we're looking for exact 16.7. We have 32 and 12 and 12.5. So 10 here. 11, 12, and 12.5 is exactly. Am I on 32? Yes, I am. Right. And draw the next side of that. All right. Final point is on 26. All right, 26 will be here, and 10. Right, 10 will be there. Right, and if I'm trying to draw my best fit line, I'll have to start a little lower because this application won't allow me to write directly on the X. Right, and go up, trying to be as steady as I can. You will have a little bit more control using your pencils, but your line should be smoother than that. And for simplicity's sake, I will use my line drawing tool to complete the curve. Right, so that part is completed, best fit line drawn. Right, so part B is completed. What deduction about solubility of X can be made from the graph drawn in one above? So what trend are we seeing? What general trend are we seeing when we look at the graph? Okay, where is my graph? The graph is below, sorry. We're seeing generally that the solubility, right, of X increases as the temperature of the solution increases, right? Because the slope, it's sloping up, right? If it were decreasing, it would slope down. So that is the trend. You're just looking at the trend of the graph. The solubility of X increases as the temperature of the solution increases, right? So that's basically to say in layman's terms, more of X can be dissolved in the same amount of water at a higher temperature. Part D now, using the equation given in 1A, right? So part 2, the same equation here. And the graph drawn, right? So using a graph as well, calculate the minimum volume of water which is required to dissolve 2 grams of X at 60 degrees Celsius, right? So from the graph, we can find the solubility at 60 degrees Celsius, right? We know that because we can use solubility graphs to find the solubility at any temperature that is on the range of the graph. And if we look at the table, we see that if we have the solubility at that particular temperature here, right, we can plug it in, and one of the values in the equation actually says the mass of water, right? And we can plug in the mass that they gave us of X, which is 2 grams, and rearrange the equation using simple math to make the mass of the water the subject of the formula, right? So let's go to our graph to get our solubility at 60 degrees Celsius, because that is what the question asks for. So what you would do in that case is you go up to your line, right? From 60 degrees Celsius, go up, see where it meets the line, and go a little to the side. And then to get your solubility, you just, oops, wrong tool, take my straight line tool to get your solubility. You just go across to your solubility axis and read off what you have there. Right? And let's count and see where we are. We have 21, 22, 23, 24, 25, 26, 27, right? So that puts our solubility at 27 grams per 100 grams of water, right? Now we can go back and rearrange our equation, right? So we can have solubility. Our equation says solubility at 60 degrees Celsius, right? And we will give that the symbol X is equal to, my typing a little small, right? Is equal to your mass of X that you use divided by your mass of water that you multiply by 100, the mass of water that was dissolved in, right? When you rearrange the equation to make this part, to make this part here, the mass of water, the subject of the formula, because that's what they want, right? They want you to get the minimum volume of water, right? And volume will be equal to mass for the water. You will have right? You type it. We have mass of X is equal to your mass of X. Sorry, this should be mass of water divided by solubility of X at 60 degrees Celsius, right? Right, because when we rearrange, right, to get your water on the other side, you will have to multiply by water on both sides, right? So you multiply by water, then to remove the solubility that will be here on this side along with your mass of water, you will now divide by solubility. So then you divide by solubility on the other side, right? And you still have your multiplied by 100 being there, right? Let me just erase this little line so that it does not confuse anyone, right? So if we input the values, we will have the mass of water being equal to 2, which is the mass of X, divided by the solubility. Some problems to write it a little close. Right, which we got, remembering, is 27 multiplied by 100. And when we input that into our calculator, we should get 7.41 grams, which is equal to 7.41 cm³, right? So we have our theory part here, which says part E, distinguish between a solution and a suspension, right? So when we see the word distinguish in our past paper questions, we know they're asking us to basically identify maybe a little bit of the similarities, but mainly the differences between the distinguishing factors between the two things that they're asking us to distinguish then, right? So you give a definition, right? It would be something that will define the two factors, but within defining them, you have to make sure and list the distinguishing factors, right? Right, so we want to talk the distinguishing factors. We want to talk about the particle size, right? That would be different. The things that are different between solution and suspension. The particle size is different. It is smaller in a solution than a suspension. We want to talk about the fact that a solution dissolves in water and a suspension doesn't. A suspension will settle to the bottom after a time. The solute will settle to the bottom after a time. A solution would not, right? And a solution is a homogeneous mixture, right? Meaning it is uniform, all the parts are the same, whereas a suspension is a heterogeneous mixture. It is not necessarily uniform, right? So let's start to make a little table. This will be the easiest way to put in, right? You don't have to put as much distinguishing factors as I may put in my table. Instead of a table, let me erase that. Let's just write it out in point form instead, right? A solution is a homogeneous mixture where, and this is a mixture where the solute dissolves in the solvent where the solute dissolves in the solvent. It is usually transparent. The particles are small. The solute particles are small. And the solute cannot be filtered out of the solution, right? As opposed to a suspension, which is a heterogeneous mixture where the solute does not dissolve. It is opaque the solute particles are larger than in a solution, right? So we're comparing exactly, or we can give the figures, right? And finally, the solute particles can be filtered out of the mixture, right? So you're giving a direct comparison, showing mainly the differences between the two. How are you going to distinguish between the two, right? And our last question in this past paper, besides temperature, state two other factors that affect the rate at which a solute dissolves. Right, so we know for sure that temperature affects the rate at which a solute dissolves. Right, I would say your one particle size of the solute smaller particle size or surface, right, area per volume ratio, right, of the solute, right? So that is how finely ground the solute is, right? And this will mainly apply, let's say, to crystals, even some powder, more powderish solutes. Smaller particles dissolve faster. right? And 2, the type of solute. I shouldn't say the type, I should really say the chemical characteristics of the solute versus the solvent, right? So in comparison to the chemical characteristics of the solvent, how is the chemical characteristics of the solute? Right? When both solute and solvent are polar, the solute will dissolve faster. Right? I hope everyone understood the past paper. That is the end of this question.